Hello again. This is Math 1120 coming to you from the College of DuPage, and this is the conclusion on our regression discussions. As always, please be an active learner as you watch this video. A question that you may be asking yourself is, how do I know the correlation between two variables is strong enough for me to conclude that a linear relationship exists between them? Another way to say this is the linear regression equation good enough to use? Although rigorous tests can answer this question, for now we will contend with a simple comparison test. So here's how you will do it. You will determine the correlation coefficient and take the absolute value of that number. That means you drop the sign, the SIGN. You make it positive. So you determine the absolute value of the correlation coefficient. You find the critical value in Table 2 from Appendix A for the given sample size. If the absolute value of the correlation coefficient is greater than the critical value found in a table, then a linear relationship exists between the two variables. Otherwise, no linear relationship exists. That means the linear relation that you found is not good enough to use, and so your best estimate of y for any value is y bar, the average of the y values. Another way to think about the procedure is to consider that if you're outside this critical value and it's a positive association, then it's good enough to use. If you're outside this on the negative side, it is good enough to use. Otherwise, it is not good enough to use, and you resort to this. Here's an example of Table 2, and you can see you have the sample size and the critical value of the correlation coefficients. And you can note here that as n gets larger, the critical value goes down rather than up. So let's apply that to a problem, and the title of this problem is An Unhealthy Commute. Okay, so they surveyed some adult Americans regarding their commute time to work, and also they administered a well-being survey saying, oh, how healthy are you, or how happy are you, what is your well-being? And so this is the data that they got from this sample. And so I asked some questions. Which variable do you believe is likely the explanatory variable, and which is the response variable? I ask you to draw a scatter diagram of the data. I ask you to determine the linear correlation coefficient between the commute time and the well-being index score. And then I ask, does a linear regression or linear relation exist between the commute time and the well-being index score? That is the linear equation good enough to use? You know what to do. Let's see how you did. Okay, so if you make a scatter plot, first of all, let's talk about which variable explains the other. Well, how happy you are doesn't tell you how long your commute's going to be, but the longer the commute, the less happy you are. So this is going to be the x and this is the y. So this is the x and this is the y. I ask you to draw a scatter diagram, and so your scatter diagram should have looked something like this. I asked you to calculate the linear correlation coefficient, and when you did that, you get that this is minus 0.981. And then the last question is, does a linear relation exist between the commute time and the well-being index? Is this good enough to use? Well, you count the number of pairs of data points, 1, 2, 3, 4, 5, 6, 7, and you look in your table and you see that the critical value is 0.754. Since the absolute value of this number is 0.981 is greater than that, it's good enough to use. And so what you can do then is you can, and we talked about this in the video, you can compute what is the least squares line. And if you did that calculation, you would find that the least squares line is WBI, the wellness being index is 69.03 plus 0. Actually that's a minus 0.04791 times your commute time, and that's the red line that we see here. And of course it was good enough to use, so I could use this to estimate values like saying, oh, suppose your commute time is 10. What do I expect your wellness being index to be? And again, there's your table 2. We're now going to spend a little bit of time, and there's more of this in a video that I point you at later, but explaining the difference between correlation and causation. Earlier in the course, we stated that there are 2 types of studies. We can have observational studies where you just go out and make notes about what's going on, and designed experiments. And so an experiment, you set things up, you have 2 groups that are pretty much alike, and you introduce a treatment on one of them and you see what happens. So if the data used in a study are observational, you cannot conclude 2 correlated variables have a causal relationship. For example, the correlation between teenage birth rate and homicide rates is actually very close to 1. But you cannot include that higher teenage birth rates causes higher homicide rates because the data are observational. In fact, time series data are often correlated because both variables happen to move in the same or opposite directions over time. You see, both teenage birth rates and homicide rates have been declining since that time, so they do have a high positive correlation, not because one causes the other. So you have to think, is there another way 2 variables can be correlated without being a causal relationship? And that is yes, through what we call a lurking variable. A lurking variable is related to both the explanatory variable and the response variable. For example, as air conditioning bills increase, so does the crime rate. Does that mean that people should turn off their air conditioning so the crime rates decrease? Certainly not. In this case, the lurking variable is air temperature. As air temperatures rise, both air conditioning bills and crime rates rise. We have one other parameter that we're going to be talking about, and that is called the coefficient of determination. And the definition of the well, first of all, we'll talk about what it is. The proportion of variation in the response variable, that's the y, that is explained by the least squared regression line, is called the coefficient of determination. So here's the definition then. The coefficient of determination, called capital R squared, measures the proportion of the total variation, the response variable, that it is explained by the least squares regression line. In other words, the coefficient of determination is a measure of how well the least squared regression line describes the relation between the explanatory and response variable. The closer R squared is to 1, the better the line describes how changes in the explanatory variable affect the value of the response variable. It also gives you insight into perhaps what lurking variables you might have or other variables you have to investigate. Just suppose that the thing that we were measuring was a club head speed and driving distance on a golf range. Well, your club head speed has a lot to do with what happens, but let's suppose that y bar, the average that you would expect to have, would be 266.75 yards. But this is the equation that we get. This is y hat equals mx plus b. And so that is the least squares line. And you see it doesn't go through the points, but it's the best least squares line that we can get. So if we take a value like 103, then what we have is there's a difference between what we would expect. And the difference is part of it is explained by the regression, that is the club head speed, and part of it is not explained. The ratio of this to this is R squared, is capital R squared. And in fact, we can actually go through an analysis like that. Here we're letting y hat be the equation of the line, and we've got these things. So we can say, what is y minus y bar? Well, that's the same thing as adding and subtracting y hat. Now, it is beyond the scope of this text, but it can be shown that if you square and add these up, things will cancel, and this is what you get. So the summation of these things squared is the summation of these things squared plus the summation of these things squared. That's kind of a subtle mathematical fact, and we're not proving it here. But if we divide both sides, then we get that 1 is equal to the unexplained variation over total variation plus the explained variation over the total variation. And so we get that R squared is the explained variation over the total variation. And that's a mathematical proof. You're not going to be held responsible for that, but that's why this is so. Now, to find the coefficient of determination, capital R squared, for the least squared regression model, y hat equal b1x plus b0. That is, we have a single explanatory variable to the first degree. All we have to do is square the linear correlation coefficient. That is, capital R squared is equal to lowercase r squared. This method does not work in general, but this is the only examples that we're going to be talking about in your course. If you want to study more of this, you can take the statistics course with me later. And again, we can see some examples here. Here you see data set A fits the regression line very well, and that coefficient of determination is very close to 1. B is not as good, but not bad, and that has a lower coefficient of determination. And C is actually kind of a bad one, and only 9.4% of the variation is explained by the regression equation. So the higher this is, the better your regression equation explains things. Note that as the explanatory ability of the line decreases, the coefficient of determination, R squared, also decreases. Here's another problem. As concrete cures, it gains strength. So here's some data. This is the 7th day strength. This is the 28th day strength. You know what to do. Let's see how you do. Okay, well, we could do many things. We can do a scatter plot. We can find the least squares line that I found up here. I'm calling that 7 and 28 respectively. You can find the correlation coefficient here, and you can find what happens if I square the correlation coefficient. Now, if I square the correlation coefficient, I get 0.75, and if I round it off, 7. That means that this explains 57.5. That means there's 42.5% of the variation is not explained. And we say, well, is that good enough? Well, we had 10 data points, so I look over here at 10, and we see that the cutoff critical value was 0.632. Since this number is less than 0.632, the equation is not good enough to use, and we will use y bar, and y bar is the average of all the y's, and it's 4625. There's some other videos I would like for you to look at in addition to this one. We'll go back to our to this spot, and we're going to look at a case study that pulls us all together called Save the Bay, which is lesson 14, and also lesson 16. There's a question of causation. This is a dark video dealing about smoking, and so try to be in a good mood when you watch it, because it's a little bit depressing, but there's much to be learned from it. And there's also a low-stakes assessment that will be due later. It's about crickets and chirping, and this asks pretty much all the questions that we've covered in our regression studies. So this will be a low-stakes assessment. I think it is 4 that will be due sometime soon. This will be posted in Blackboard for you to consider. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.